Welcome to the presentation on race conditions and hazards in digital circuits. In this video, we will explore static and dynamic hazards, which are critical concepts in designing reliable digital systems. Let's begin by defining race conditions. A race condition occurs when the output of a digital circuit depends on the relative timing of input signal changes rather than just their logic values. This timing dependency can lead to unpredictable outputs and circuit instability. Therefore, the key points to remember are that race conditions make the circuit timing dependent and produce unpredictable outputs. This can also lead to circuit instability. There are primarily two types of hazards that we need to consider: static hazards and dynamic hazards. Static hazards involve unwanted glitches when the output should remain constant. These are further divided into static zero hazard and static one hazard. Dynamic hazards, on the other hand, involve multiple output transitions when only one transition is expected. So, in a nutshell, static hazards produce unwanted glitches, whereas dynamic hazards result in multiple unwanted transitions. Now, let's discuss static hazards in more detail. There are two types of static hazards: static one hazard and static zero hazard. A static one hazard occurs when the output momentarily goes to zero, but it should actually remain at 1. Conversely, a static zero hazard occurs when the output momentarily goes to 1, when it should actually remain at 0. The waveform diagram shows a static one hazard. Notice how the output briefly dips to a low value when it should remain high. These unwanted momentary transitions are the key characteristic of static hazards. Now let's turn our attention to dynamic hazards. Dynamic hazards occur when the output changes more than once during a single input transition, when only one change is expected. So, instead of a clean transition from 0 to 1 or 1 to 0, the output oscillates before settling to the correct value. This results in multiple unwanted transitions during a single input change. The waveform diagram illustrates a dynamic hazard. Notice how the output transitions multiple times before settling down. What causes these hazards in digital circuits? The two primary causes are propagation delays and timing skew. Propagation delays are the time it takes for a signal to propagate through a gate. Since gates have finite switching times, different path delays cause signals to arrive at different times. Timing skew refers to variations in signal arrival times due to circuit asymmetries, such as unequal wire lengths and loads. Therefore, propagation delays are due to gates having finite switching times, and timing skew is due to unequal wire lengths and loads. Let's consider an example to understand how to detect hazards. Here's a Boolean function. F equals A and B plus A and C. Consider when it changes from 1 to 0, B is 1 and C is 1. In this scenario, a static one hazard is detected. When it transitions from 1 to 0, both product terms AB and AC may momentarily become 0 due to propagation delays, which causes an output glitch. Finally, let's look at some common methods to prevent hazards in digital circuits. Two effective methods are the Strobe method and using consensus terms. The Strobe method uses synchronous timing to sample outputs only after all transients settle. Clock-based synchronization eliminates timing issues. Consensus terms involve adding redundant product terms to the Carnot map to eliminate hazards, which helps bridge adjacent prime implicants. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.